The voltage pulse described by the following equations is impressed across the terminals of a 0.5 microfarad capacitor as given below. So you can see we have a voltage V of t equal to, you can see we have about three voltages defined across the terminals. We have zero V of t equal to 0 for t less than or equal to 0 seconds. So when t is less than 0 seconds or equal to 0 seconds, the voltage is 0. Then for V of t equal to 4t, the for time greater than or equal to 0 seconds or less than or equal to 1s, our V of t equal to 40. And then our V of t equal to 4 exponential minus into bracket t minus 1 for time greater than or equal to 1 second. So you can see that we have voltage described in the time domain, and then we can see the respective times here. Now, before I continue, I want you to know that if you have any questions, you can just send me a message. So the question says, derive the capacitor current, capacitor power, and then capacitor energy, and then sketch all as a function of time. So once we find the capacitor current, we're going to sketch as a function of time. So, and then the same thing goes with the power, and then the same thing goes with the energy. All right. So the first thing you want to do is this. You will find that we can easily sketch the voltage time graph, okay, the time waveform for the voltage before we go ahead. So at the beginning, when V of t is equal to 0, okay, our time is less than or equal to 0. Okay, so at this particular point, we do not have much representation, any representation on the graph. Okay, okay. Then the second voltage expression is V of t equal to 4t. At this particular point, our time is greater than 0 and then less than 1. Okay, so less than or equal to 1. So when time is greater than or equal to 0, you can say t equal to 0. When t is equal to 0, you can put t equal to 0 in this particular expression. Your V of t will be equal to 0. So you can have a point when t is 0, V is 0. So you can have this point as t equal to 0, V equal to 0. Also, when t is equal to 1, because we can say that t is greater than or equal to 0, less than or equal to 1. So when t is 1, what will be our V of t? It will be equal to 4. So when t is equal to 1 at this point, our V of t will be equal to 4. So you can see this is up to 4 here. You could join these 2 points together to form your graph. So this is when t equal to 1. Also, when V of t is equal to 4 exponential minus t minus 1, our t is greater than or equal to 1 second. So now for t greater than or equal to 1s, we have this voltage time function. So V of t equal to 4e exponential minus t minus 1. The first thing you want to start with is 1. When t is 1, you have, when t is 1, so you have 1 minus 1, right? It becomes 1 minus 1. 1 minus 1 will give us 0. So you have 4 exponential 0. Exponential 0 is equal to 1. So when t is 1, just like we said, our V of t will be equal to 4. So at this point, we have this. What happens when t is 2? When t is 2, you have 2 minus 1 here. 2 minus 1 gives us 0. So you have 4 exponential 1. All right, and you know that exponential e is always equal to 2.718. Okay, so if this is our exponential, it simply means that you can say we have 4 multiplied by, so we can say we have 4, there is minus, okay, so 4 exponential minus 1. Now it's going to be 4 exponential minus 1. All right, so if you punch your calculators to find 4 exponential minus 1, you will get something. All right, okay, so if we 1.472, beautiful. So approximately that is what we have when you do that. So at value of 2, if you come to this place at the value of 2, you will find out that this is 2. When t is 2, you get a value here. If you trace it to this end, you should have a 1.47 here. So when t is 3, you just do the same thing when t is 3, when t is 4, when t is 5. You can keep doing that until you get to a point where you have to stop, okay, where, because they say t greater than or equal to 1. So t can go as far as any value, but then Once you get it to up to 0 here, you can stop. When you have t equal to 6 is when we have our exponential to be equal to 0. When we have this v of t equal to 0, so you can stop at that particular point, and then we can continue. So that is for the voltage graph, and we're going to repeat this particular procedure for when we find the capacitor current, when we find the capacitor power, and then when we find the capacitor energy. So let's take it to the next level now. All right. Now, what you have here is the capacitor current. You know that when you want to find the capacitor current, our I is always equal to C divided T. So what you will see here at the moment is, since we have our V and we have our C here is 0.5, what you will see here is that for the first one, we have C is 0.5 here, divided T, this is a constant, this is 0. So if you differentiate 0 for the first 0 we have here, you will obtain 0. Okay, so you have 0.5 multiplied by 0, because divided T here is 0. All right, that gives us 0 microamperes. Okay, also we go for when our V of T is 40. When V of T is 40, what is going to be the current? Current is going to be C, which is 0.5, multiplied by divided T. If you differentiate 40, it will give you 4 with respect to T. Okay, if you differentiate with respect to T, it will give you 4. So 0.5 microfarad multiplied by 4 will give us 2 microamperes. Okay, can you see that here? Also, when we have V of T equal to 4 exponential minus T minus 1, this automatically gives us, if you differentiate this, it gives you minus 4, by the way, because of this minus here. Minus 4 exponential T minus 1 is what you get when you differentiate, when you find divided T with respect to T for this function. So multiply that by 0.5, you obtain minus 2 exponential T minus 1 microamperes. Okay, so these are the various currents we have for these various voltages for these capacitance 0.5 microfarad. Now the question then comes, we have these time limits. So how do we plot our time wave form for the capacitor current? All right, so when t is less than 0 is the first one here, so automatically our I of t will be 0 when t is less than 0. So right now, as you can see here, we don't have a place for that on the graph too. So now what happens when t is greater than 0 and less than 1? So between 0 and 1, what is going to happen between 0 and 1? You can see also here that this has no t, so there's no place we can substitute t here. So our I is just constant here. Okay, the current is just constant when voltage is 40. Our I of t is just 2 microamperes, so it's constant. You just go where is 2 on our graph, because we are plotting the graph of current against time. So you just go to where we have 2, and then you put your 2 here. So that 2 is constant, and it's going to continue until something changes. So the 2 will continue until we get to a point where something changes. All right. So then also we do have I of t equal to minus 2 exponential minus t minus 1. At this particular level, our t is greater than 1, as you can see from the question given to us. T is greater than or equal to 1. So when t is 1, we have 1 minus 1 at the top here. When t is 1, we have 1 minus 1, 2 exponential 0. Exponential 0 will be equal to 1. So your I will be minus 2. When t is 1, your I will be minus 2. So that is why you can see here we have at t equal to 1 here, our I current is equal to minus 2, and then it's at this point. So it's going to be here. So you take note of these, all right? So you will find out that we have gotten the second point on this particular graph. Then you go ahead and say, what happens when your t is 2? When t is 2, you have 2 minus 1. 2 minus 1 is 1. So you have 2 exponential minus 1. So if you punch your exponential minus 1 multiplied by minus 2, what would you get? It's just going to be minus 2 multiplied by 2.718 exponential 2.718 raised to power minus 1, and then the answer is minus 0.76. So you find out that minus 0.76 is going to be somewhere here just before 1 on the current graph. So it's going to be somewhere here. So you can see it is somewhere here. All right. The same thing, you put 3 here when t is equal to 3. You put that here. So you keep getting different points, and then you keep getting different points until you get to a point where you're going to stop when you have the curve coinciding with the horizontal axis. So you join them together, and so you can see this is exactly how to sketch your capacitor current as a function of time. This is exactly how to do that. All right. So let's take it a step further. If we do that, we go forward. Now we want to find power. We have dealt with current. We want to find power, and we do know that our power is the same thing as voltage times current. So now that we have current and we have our voltage, we're just going to multiply voltage and current together to obtain our power. All right. So once we do that, you'll find out that when voltage is zero and current is zero, you have zero multiplied by zero, and your power will be equal to 0 microwatt. Can you see that? Good. And the time function remains as, the time limit, the range remains t less than or equal to 0. All right. For voltage equal to 40, and then current will be equal to 2 microamperes. If you multiply current and voltage, you have 40 multiplied by 2 micro, that gives you 80 microwatt. The same thing for 4 equal to 4 exponential minus t minus 1. Multiplied by the current at that point, which at that voltage is going to be minus 2 exponential minus t minus 1. If you multiply both of them together, you obtain minus 8 exponential minus 2t minus 1 microwatt. So you can see that we have obtained the powers for the capacitor, okay, 0.5 microfarad capacitor given this voltage functions. We've obtained the power for those. So if you want to plot the power curve, the time wave form for the power is going to be power on the vertical axis. When power is 0, our time is also 0. Okay, so you can see here we have power equal to 0, and then time equal to 0. So that's a point that we have here. Also, when power equal to 8t, what is going to be our time? When power is 8t micro, our time is going to be greater than 0 and less than 1. Greater than or equal to 0 and then less than 1. So, for example, for t equal to 0, we know that our power will be equal to 0 automatically for t equal to 0. So we already have that here. So for t less than 1 or equal to 1, let's start with 1. All right. So we can do 0.1, 0.2, 0.3, 0.4. You can do all of those, but it's not important for us here. We can just pick 1 and 2, and then just keep using whole numbers to avoid having messy calculations. So we don't need that much details. You can just pick 1, 2, 3, 4. All right. So starting with 1, since we are dealing with less than 1, so we're going to, the limit here is 1, maximum limit is 1. So if you put 1 here, you will see that your power will be equal to 8. So at 1, the power will be equal to 8 at this particular point. Can you see that? So you can connect 0 to 1 straight up from 0 to 1 here. Okay, you can see that. So also you can just pull this up and then you connect them together. Also, when we go to voltage function of 4 exponential minus t minus 1, so we dealt with when voltage is 0 and when voltage is when voltage is 40. So for the third one, 4 exponential minus t minus 1, our current is minus 2 exponential minus 1. If you multiply both together, you obtain 8 minus 8 exponential minus 2 this, and then at this level, our limit is t has to be greater than 1. We already know that when t is 1, we are here, so we do it for t greater than 1. When t is greater than 1, what do we have? First of all, the first value greater than 1 is 2. We don't want to do 1.1, 1.2, 1.3 for all the graphs. So you just deal with 2, and then 3 and 4, and so on and so forth. So when t is 2, you have 2 minus 1, you have 1 left, and you have exponential minus 2. So exponential minus 2 is 2.718 raised to power minus 2 multiplied by minus 8. You find out that there is a value here, and then when t is 3, there is going to be another value here. When t is 4, we obtain a value here until we get to the final point. All right. So as soon as you're done with your power curve, the next thing you want to do is to go ahead and find the energy. All right. So we do know exactly how to find energy when we talk about capacitors. Okay. So the energy is usually half CV squared, like we discussed in the previous slides. So we know our C is 0.5 microfarad. We know that. We also know that our V, we have V, respective V's, so different functions, but 3 of them. So we can have for the first one, half CV squared is going to be 0, as you can see. The second voltage for 40, you can see we have half 0.5 micro times 4t squared is going to be 16t squared. So you can see if you expand that, you have 4t squared here. And also, if you check the last one, for exponential minus t minus 1 multiplied by half c, you're going to come up with what we do have here with this micro. There's a micro here, 10 raised to the power minus 6. So you probably, already know what we're going to do. For t greater than, less than, equal to 0, our energy is 0. So at this particular point here, when the energy is on the vertical axis and t is on the horizontal axis. So when t is 0, we can see the energy is 0. So when t is greater than 0, less than or equal to 1, you can just pick 1. All right. So if you put 1 here, you have 1 squared. That is 1 times 4 is 4. So you can see we have a point here. Now you will find out that this is not a straight line, right? Why is it not a straight line? For the voltage, we just connected from 0 to 4. Why? Because 4t here is a linear equation. It's a straight line equation, all right? It's a linear equation. But if you come here, you find out that 4t squared here for energy, this is not a linear equation, right? This is supposed to be this is a quadratic function. So you will find out that is the reason we have a curve from 0 going to 4. We have a curve, all right? So from that particular point, you will find out that we'll keep getting quadratic function also for the third voltage function. When we find energy for that, you will find out that the energy function keeps giving us values that we can keep connecting until we get to point. So once we get to the horizontal axis where we coincide here, we're just going to stop. We're going to stop. Okay, so this is an exponential function. This is an exponential function. This is an exponential function. That is why this is going exponentially down. But this one is a quadratic function, by the way. That is why it is called. And this is a straight line. Okay, that is why it is a straight line here. Right. Of course, this is a constant, and it's going to be a straight line like that. All right. So I think this summarizes the basic details for solving this problem. And we have been able to find, according to the question, they asked us to derive the capacitor current and sketch its function sketch it as a function of time. Derive the the capacitor power, which we did here. Sketch it as a function of time. Derive the capacitor energy. Sketch it as a function of time. And then this brings us to where we are here. Okay. So find the interval of time when energy is being stored in the capacitor. Find the interval of time when energy is being stored in the capacitor. So energy is being stored when the power is positive. All right. We mentioned this in one of the slides when we were talking in previous classes. Energy is stored when the power is positive, based on all the discussions we've had in the original assumption. So when power is positive, that is when energy is stored, and we are looking for interval of time when energy is stored. So that will be when t is greater than 0 seconds and t less than 1 second. Okay, for the first voltage function. Because if you look at here, the first voltage function, we cannot have interval of time when energy is stored here. So for v equal to 0, there is no energy stored, because the time interval we have here is less than 0. It is negative, so energy cannot be stored because the time interval is negative. Okay, it's less than 0. So we're going to have energy stored starting from t greater than 0, less than 1. Okay, so when t greater than 0 and less than 1 is when energy is going to be stored for second voltage function, and for the first one, no energy is stored. And then for the other one, for the last voltage function, energy is going to be stored when time is greater than 1. All right, so that gives you a more understanding of what we're talking about. Then there is another question regarding this same question that says that we should evaluate the following integrals and comment on their significance. Okay, so still on the same question, we have some integrals given to us. We are supposed to evaluate those and then try to make some comments on them. All right, so the same voltage functions, we have been given this integral of 0 to 1, power multiplied by delta t. Okay, power dt. Okay, so, and you do know that our power, we have power. If you flip back a bit, you can see that we obtain power here. Here are the powers that we have. So the power of zero here, we're not going to deal with this because, you know, I mean, it's zero, multiply, everything is just going to be zero. Integral of that is just going to be one. So here we're not going to deal with that, but we're going to start with 8t microfarad right now. So for the 8t microfarad, we have 8 micro is 8 times, micro means 10 raised to power minus 6, by the way. So 8 microfarad will mean 8 times 10 raised to power minus 6. We have 0 to 1, and then we have our t here, all right? So this 8 times 10 raised to power minus 6 as a whole is a constant. You can bring that out. If you integrate your t, you have t squared over 2. So from 0 to 1. If you put 1 here, you have, you know, you can just carry out the mathematics and you put 1 here and you put 0 there, and then you subtract when you put 0 there, you subtract it from when you put 1 there, and then you obtain 4 microjoules. So this is the energy stored in the capacitor when t is greater than 0, less than 1. Because if you notice, what we just did here is that we pick the energy when we pick, where is it? We pick the power. You can see we have the power equal to 8t here, right? So and then after we integrate the power, you're going to have your energy. When you integrate power, you usually have energy, right? So it simply means that whatever you obtain as after the integration is going to give you the energy when t is greater than 0 and less than 1 for this time range. Then we're going to go for the third one, which we have for t greater than 1. All right. So the concept and the story is also going to be the same. All right. For that, you can also find for, you know, 1 to infinity here. If you integrate from 1 to infinity, you should get something. All right. So for when t is greater than 1, what are you going to obtain? When t is greater than 1, what are you going to obtain for this particular scenario? When t is greater than 1, we have the formula for power already, which is here. You just pick this formula for power here. Okay, dt. When you integrate it, what do you obtain? Whatever you obtain is going to give you the energy delivered by the capacitor when t is greater than 1. Capacitor phase shift between current and voltage waveforms. So we're going to talk about current and voltage waveforms, and then the capacitor phase shift. So there are two things you need to know, and those two things are these. Now, current leads voltage by 90 degrees in the capacitor. Current always leads voltage by 90 degrees, and voltage lags current by 90. Of course, if current is leading by 90, leading voltage by 90, that means voltage is lagging, you know, by 90 in the capacitor. So let me quickly show you what that looks like on the waveform here. I can explain to you guys some time ago. This entire waveform you're looking at here, the full circle is up to this point, from this point. And that full circle is 360 degrees, okay, when you consider angle. So this is half of the circle here, all right? So this is usually referred to as pi, and this is usually referred to as 2 pi, 360 degrees, because pi is 180, okay? So this is a voltage waveform. The orange graph, orange curve is the voltage waveform, and then the current curve is the current waveform, right? So if you have certain values of current and certain values of voltage and then certain values of time, and then you plot them into the I of t equal for the current, if you plot it into this I of t, this is what kind of waveform you're going to obtain for the current. If you pick the voltage waveform and you plot those values, random values you have, you're going to obtain this kind of curve for your voltage. So what you can see here is that the current curve is meeting the horizontal axis at the middle here. This middle here is half of the entire journey to this particular voltage. All right. So, and then you will see that the voltage is starting from 0 on the positive axis here, but our current is starting from where? From 90 on the x-axis here. So when you draw this time graph for time waveform for voltage and current, you will find that current is ahead of voltage by 90 by pi over 2. Current is ahead of voltage by pi over 2, which is also referred to as 90 degrees here. All right. And then the voltage is lagging behind current by the same amount, which is pi over 2. So when we are dealing with phase shift between current and voltage waveforms, you should understand how this shift works. So this 90 goes on, there's another 90 here, there's another 90 here, and then the 90 just keeps continuing like that, another 90 between the current and the voltage. So always, anytime on that particular graph, the current leads voltage by 90, in the capacitor, and then voltage lags current by 90 degrees in the capacitor. I of t is equal to C dV dt, dV dt here. So by carrying out simple integration here and simple arithmetic, trigonometric rearrangement here, you obtain I of t equal to I max cos wt. Okay, so we've talked about something like this too before in the previous courses, in the previous slides. So let's take it a step further. Okay, so now we want to talk about series and parallel capacitors. Okay, when we were talking about resistors, you will remember that we talked about series resistors, we talked about parallel or shunt resistors. We will also talk about series capacitors and then parallel connected capacitors. So when we have those, there is a way to prove all of those, but I don't want to take you through the proving. You can just go through these. Our voltage is always 1 over C integral of current dt. So if you have two voltages and then you add them together, this is what you are going to obtain, and so on and so forth. So your C total will be equal to 1 over C1 plus 1 over C2. So what you find here is that you can rewrite these as 1 over C total is equal to 1 over C1 plus 1 over C2, right? You can write the 1 over C1 plus 1 over C2. So this is the same thing as this, you know that already. So if you make C total the subject of the formula, you just have, what you have here. You realize that the series connected capacitors, they behave like parallel connected resistors. That is what you will see now. The series connected capacitors behave like parallel connected resistors, because when resistors are connected in parallel, that is when we have expressions like this. But when capacitors are connected in series, we have expressions like this. Okay, so this is also just a very simple way to show what the whole of this would look like when we have capacitors connected in series. Okay, so when capacitors are connected in series, this is how you can represent them. This is how you can represent them in a circuit. When they're connected in series, each capacitor has its own voltage. So you have V of 1 here, you have V of 2 here, you have capacitor 1 here, you have capacitor 2 here, and then you have the entire voltage source here. All right, let's try to take it a step further. What happens when these capacitors are connected in parallel? So when we have these capacitors connected in parallel, what can we say about that? What happens? At the end of the day, you're going to use your current here to find that expression. So when we're finding for series connected, you use voltage 1, voltage 2. For shunt connection, we're going to use current 1, current 2. Why are we using current 1, current 2 here? Because when they are connected in parallel, you will see that they have different currents. So you're going to find different current 1 and current 2. When they are connected in series, they're going to have different voltages. Okay, so that's why we have to look for voltage 1 and voltage 2 for the series connection. So if you do all of those, at the end of the day, you will find out that your C total will just be equal to C1 plus C2. Again, this is how we deal with resistances in series. All right, so the way we deal with resistances in series is the way we're going to deal with capacitors in parallel, connected in parallel. Okay, so you just simply add the capacitors together to get the total capacitance. This is also straightforward. So what you will find here is that these capacitors, they are in series. All right, so and then if they are in series, remember this is how we usually find the capacitors in series. For resistors in parallel, we usually say you multiply the two resistors together divided by the addition. So for capacitors, since capacitors in series behave like resistors in parallel, the capacitors in series, the effective capacitance will just be C1, C2 divided by C1 plus C2. All right, like I mentioned earlier, you treat them that way. Also, for ones in series, okay, this is what it looks like when in parallel. When capacitors are connected in parallel, this is what it looks like. Okay, so total capacitance in parallel will just be addition of all the capacitance that we have connected in parallel. This is very important for us, so pay attention to them. We'll use them in solving as many problems as possible as we get on. Okay, so very briefly, we're just going to quickly try to solve this question together. Find the equivalent capacitance for the following circuit. Okay, so this is going to be a piece of cake for you guys. For example, what you will find here is that these two capacitors, are they in series or parallel? These guys are in parallel, right? So if they're in parallel, you just have 2 plus 2. So eventually what you have here is just 2 plus 2, and then what you have here will be 4 microfarad at the end of the day. This is just going to be 4 microfarad here because they're in parallel, you just add them together. Okay, so this is like the capacitance connected. Okay, also this is connected here. Excuse me. So then we come down here. We have another capacitor here. All right, what is the value of this effective capacitance here? Okay, the value of the effective capacitance here would be the value of this capacitance in the second. This is 1, this is 2, and then this is 3. So the value of the one in number 2 will, since these ones are in parallel, they are also in parallel. This is parallel. So you have 1 over 3 plus 1 over 3 plus 1 over 3. So the effective capacitance in this connection here will be 3 over 3, and that would just be 1. So this gives us 1 microfarad. Okay, so when you connect these together, you get just 4. When you find the equivalence of these, you get 1. So what about what happens when you find the equivalent of these? You have 1 over 3 plus 1 over 3 plus 1 over 3 plus 1 over 2, because these guys here are also connected in parallel. All right, so this gives you 4 over 3 microfarad, isn't it? Yes, 4 over 3 microfarad is what you have here. Okay, so if you have that, then you can see that you have converted all of this circuit into this circuit, and this particular circuit you're looking at here is in series. When we have series connection, we treat them like they are connected. We treat them like they are connected in parallel when we have resistors. So 1 over C equivalent here would then become 1 over 4 microfarad plus 1 over 1 microfarad plus 1 over 4 over 3 microfarad. If you solve all of these mathematically, you're going to obtain C equivalent to be 1 over 2 microfarad as the final capacitance for this particular circuit.